Okay, so we have introduced the definition of the closure of FDs as well as the closure of attributes. And next, let's do an example together again. And we have a question shown here. Given a relation R equals to A, B, C, D, E, we have 5 attributes. It's a relation, right? And we have a set of FDs, the function dependencies. The S is a set, S covers, B implies CD, D implies E, B implies A, E implies C, and AD implies B. We have several sub-questions. The first one is B implies E in the closure of S or not? B implies E is FD, right? The closure of S denotes the closure of FD sets. And the second one is D a key of a relation or not? The third one is AD a key of a relation or not? And the last one is ADE a candidate key of the relation or not? Here the candidate key denotes a key candidate. In other words, can we say ADE is a key of a relation or not? Okay, so let's do this question one by one together. Before I show you the answer, I'd like to suggest you pause the video here and you can do this as 4 sub-questions on your paper by yourself first. And then you can check with your answer with mine and you can see which part you may have some problems. Okay, let's pause the video here. Okay, I hope you have the answer on your paper already. Then let's do the example together. And we can do the problem 1 first. Let me change the color of the user red instead. I'm going to change the format, the font size to 40 as well. Right. So the first question we have is to check if B implies E is in the S closure or not. We have 2 ways to do this, right? One way is to use the Armstrong's axioms to calculate the closure of S first, and also find if B implies E is in the closure or not. This is one way to do this. Here I'd like to use another way to check if B implies E is in the S closure or not. So we check, let me change this one. So we check B implies E is in S closure or not by checking if E is in the B closure or not. You know what I mean? You know what I mean here, right? So instead of checking this FD is in the closure S or not, we check if E can be implied by B based on the existing FDs. If E is in the closure of B, in other words, we can get B implies E, right? Based on the existing FDs. And we can prove B implies E is in the S closure. If we cannot derive that E is in the B closure, then we can say based on the B we cannot derive E, right? So the next thing will be how can we calculate the B closure? Right? How to calculate the B closure? Then we need to use the algorithm we showed before, right? We do this in an iterative way, right? So we have loop 1, right? Right now we have x equals to what? X equals to B, right? We start loop 1 here. Inside loop 1 we have multiple FD to check. Let me change another index number. We check FD B implies CD, right? Because B is in the X, CD or not, then we can update X equals to what? X equals to B, CD, right? Then we check D implies E, and we update equals to what? B, C, D, E, right? Because we have D in the X, E is not, then we need to add the E into the X set, right? And then we can check another FD, it is B implies A, right? Because B is in the set, A is not, then we update what? We add the A into the X set. We have A, B, C, D, E, right? Then we check E implies C. We do nothing, right? Because we have C already. The last one will be AD implies B. We do nothing, right? Because we have B already. So exchange it. 1, so we start loop 2, right? Then we can have loop 2. We have x equals to what? X equals to A, B, C, D, E, right? And we do this all the checking again. We know in this loop we will do nothing, right? You can check this by yourself. We do nothing in this loop, right? So because x doesn't change in loop 2, right? You can check this by yourself. So we return x closure, right, equals to what? Equals to A, B, C, D, E, right? So based on the closure of this x or the B attribute, right, we have the closure of B equals to A, B, C, D, E, right? We find that E is in the closure of B. Therefore, we can say B implies E is in the S closure, right? So this is the answer for the sub-question 1 we can provide. Instead of checking B implies E is FD in the S closure or not, we check if this E attribute is in the closure of B or not. If so, then we can conclude B implies E is in the S closure. Because based on what we do here, we can find given B we can derive E, right, with the existing FDs. Okay, so this is the sub-problem 1. I hope you can follow me, right, and know that you can check the answer with yours on your paper and to see if it is correct or not. Okay, so this is the sub-question 1. Let's do the sub-question 2 instead. So in the sub-question 2, we want to check if D is a key of the relation or not, right? I hope you still remember the definition of the key, right? We check D is a key of R or not. So we by checking what? We check if D is a key of the relation or not. We need to check two things, right? If D closure covers all attributes of R or not. Right? Besides this, we also need to check none of D subset none of these subsets their closure can cover all the attributes, right? Of relation R. So we need to check two things. The first part will be we need to check is if the D closure can cover all the attributes or not. And we also need to make sure none of these subsets their closures can cover all the attributes. Because the D is one single attribute, it doesn't have any subset anymore. And so for the second condition, we can ignore, right? We can focus on the first condition in the answer. So we need to check if D closure can cover all the attributes or not. Then what we need to do is to compute the D closure, right? So we need to follow the same process as we showed before by using the algorithm we provide in the slides. I think you can do this by yourself. I can provide the answer in a faster way, right? We can provide x equals to d, right? And we do this in an iterative way. We check all the FDs and compare the left-hand side with x and also the right-hand side with x. So we do the first loop, b implies cd, b is not in the c, b is not in the x, cd is not, right? We do nothing because b is not. Then we move to the next FD, d implies e. We have d here, right? Then we need to add e into the x. Then we have b implies a, we do nothing. E implies c, we have e here, c is not, we need to add c here. Then we have ad implies b. We don't have ad, right? We ignore this. And then we start the second loop, b implies cd, we do nothing, we don't have b, right? D implies e, we have e already, we do nothing. We have b implies a, we don't have a b, right? We do nothing. We have e implies c, we have c already, we do nothing. We have ad implies b, we don't have a, right? We do nothing. Because in this loop, this x is not changing, therefore we can return the closure of this d will be equals to what? Equals to dec, right? Or we can change the order. This one should be equal to cde, right? So since the closure of D doesn't cover all the attributes, so we can say D is not a key of relational, right? So this is the answer to the problem 2. D is not the attribute, D is not the key for the relation, because the closure of D cannot cover all the attributes. It's not a super key, not to mention a key, right? And this is the answer. You can compare with yours to see if you are correct or not. And let's move to the problem 3.